So, last time we discussed use of deflection in a charged particle's motion when a magnetic field is applied. We have done the theory part of it. If you have a magnetic field, uniform magnetic field, and a charged particle enters perpendicularly, then it goes in a circle. We calculated the radius and the angular frequency, and if there is a component of velocity along the direction of magnetic field, then the particle continues to move in that direction without any change in the velocity, at the same time going in circles in the perpendicular plane. So, ultimately it goes in a spiral type of structure. So, those things we discussed, and then how an accelerator lab uses this deflection to split the accelerated beam in different directions, in the desired directions, by putting a magnetic field and adjusting the magnitude and the directions. One more application I have in mind, and that is E-beam evaporation. In many of the research areas of physics, chemistry, material science, biomedical applications, one needs thin film deposited on some substrate. And suppose you need a thin film of gold or any other metal, then one way, there are various techniques of making thin films, but one way is to vaporize it, heat it, so that that solid becomes vapor, and then the vapor goes up and you put your substrate somewhere, and this vapor goes and gets deposited on the substrate. So, this is a kind of thermal evaporation. So, essentially what we are telling, you have this substrate, the base material on which this thin film will be deposited, and then the solid is here, and somehow it is to be heated to temperatures, so that it melts and finally it boils, and then it comes to the gas phase, and that vapor that goes in all directions, and then part of it which falls here gets deposited, and then you control everything so that you get the desired thickness, the desired homogeneity and all those things. Now, this heating, one way is to put a heater there and create high temperatures, so that is one way. The other very cute and very effective and very simple thing is using electron beams, So, the setup is something like this. The setup is something like this. It is you have a crucible just like that. You have this crucible, and then this is the substrate, and then it is in a chamber in which you evacuate the chamber, low pressure, low air pressure, vacuum. So, you have somewhere some outlet, and you can connect a vacuum pump here, and then you will evacuate this, and then there is a circuit here. You have an electron gun. You know what is electron gun? A filament which is heated to some temperature, so that electrons come out. So, electrons come out from here, and there is a circuit for heating and all those things will be there. It can be an AC, whatever, it is to be heated so that electrons come out. Then you have another circuit where you have, let us say, some kind of a obstacle, a metal with some hole in it. So, the electrons can go through this hole, and this is at high potential. This is at high potential, right. So, the idea is that once the electrons are emitted from here, which is at ground potential, this is at say 0 potential, and with the same ground this is at high potential. So, you have electric field, and that electric field exerts force on the electrons, changes their speed and kinetic energy. So, this is small e times the total potential difference. This will be the kinetic energy obtained, half mv square. So, if you have a good potential difference, say 10k or like that, you will have corresponding kinetic energy. So, the electrons will have some good speed. Electrons are very light, and therefore, if the kinetic energy is given, since this mass is very small, the speeds can be very high. So, these electrons with high speeds come here, high speed, and then there is a magnetic field, then there is a magnetic field, then there is a magnetic field here. Let us say, I do not know if it works. If it is this way, that means the field is going into the board, this is velocity. So, V cross B will be in this direction, it is negative, so it will deflect, yeah, correct. So, it will deflect here, and then it will deflect, and the entire arrangement is made in such a way that this beam finally falls in this crucible. So, the magnetic field is now bending. So, that same situation, if you have a magnetic field, a charged particle comes in perpendicular direction, then it bends, and the entire arrangement ensures that when it bends, it goes and hits this this material, solid material here, and this kinetic energy which is gained through this acceleration here, that is deposited here, that raises the temperature, and that melts and then finally evaporates this metal in seconds. You just switch on the system and it falls, and in seconds you get these vapors, and then you deposit it. So, that is e-beam evaporation technique, which is widely used in laboratories, research laboratories. Now, next thing I will be talking is even more interesting, and this will be dealing with non-uniform magnetic field. Okay. So, I take few examples. The first one is on cosmic rays. What are cosmic rays? Cosmic rays are fast moving charged particles which are created outside the earth, maybe from the sun or some other mechanisms, but outside the earth they are created and then they move in space. So, that is cosmic rays, and some of them head towards the earth also. They are produced and then they move in all directions. So, some of them may head towards the earth also, and most of these cosmic rays particles are protons or some mesons, and the speeds are pretty high. The speeds are pretty high, and if they directly fall on our body, it may be very harmful, but we are saved. We are saved by the magnetic field of the earth, right. So, you have this earth itself has a magnetic field. If this is the globe, this is the north pole, south pole, then you have magnetic field, and magnetic field is something of this sort, This is the direction, this is the direction, like this, this is the direction. Geographical north, magnetic south here, so lines are entering, and geographical south, magnetic north, so lines are coming out from here. So, it is kind of, for large distances, is kind of a dipolar field, a small magnet, a small magnetic dipole near the center, that is one model of having this kind of magnetic field. So, suppose there is a cosmic particle and coming with velocity v. So, what happens because of this magnetic field? What happens because of the magnetic field? You have magnetic field here, this is the direction of magnetic field, and here is the velocity. So, v and cross b. So, this will be perpendicular to this plane. V is in this plane, velocity of the particle is in this plane, magnetic field that is here is in this plane. So, V and B both are in this plane. So, V cross B will be perpendicular to V, also perpendicular to B. So, if it is perpendicular to this V and this B, then it has to be perpendicular to this plane, and V cross B here is coming out of the plane. So, if it is positive charge, there will be a force q times V cross B, that will be force, and it will deflect this particle, right, and it will deflect is such a way that if it is going this way, it will turn like this, it will turn like this, and you have magnetic field all over. So, in this magnetic field, when this particle is moving and turning, then the chances are that the particle will not reach the earth's surface, and then it will turn and it will go somewhere in the space. So, we are saved with many of the cosmic ray particles. The total number of cosmic particles reaching the earth is much smaller because of this magnetic field. What about particles which are heading along this direction, along this ns direction? If the particle is coming like this, and then it enters here, and magnetic field is largely vertical here near the poles, the magnetic field is vertical. If you go at some distance, if you are on this line, right, suppose you have a dipole here and you are on this line, the magnetic field everywhere is this way. Okay. So, the particle is coming, magnetic field encountered, no problem, because V cross B is 0. For these particles, V cross B is 0, velocity is in this direction, particle is coming vertically, it is trying to hit the earth. Here also vertically it was trying to hit the earth, here also it is vertically trying to hit the earth. Here the magnetic field was nearly horizontal, and therefore, this V cross B could deflect, but here this is the direction of V, same is the direction of B. So, V and B are in the same direction, cross product is 0, and these particles which are heading right on this line, they will not be deflected by the magnetic field. Now, this is an observation, this is observation using some satellites, some experimental equipments there, that the total number of cosmic particles hitting the earth's surface near the polar regions, it is much larger than the number of particles hitting this equatorial regions or other places. So, it is called latitude effect. The number of particles hitting per unit area, per unit time is different at different places on the globe. Near the poles it is high, and near the equator it is less. So, this is the effect of magnetic field. Of course, the atmosphere itself is another shielding. When it enters the atmosphere, the molecules are there, the air molecules are there, then these particles hit them, transfer some kinetic energy, their own kinetic energy is reduced, and they become harmless even if they reach earth's surface. So, this is one thing. So, suppose you have a magnetic field which can be shown by these kinds of magnetic field lines. So, non-uniform magnetic field, the field strength is high here, all these lines are going through this small area, number of lines per unit area is quite high here and less here. So, the magnitude is increasing as I am going to this direction or I am going in this direction. Magnitude is very high here and relatively low here, and direction is also changing. Here this is the direction, here this is the direction, here this is the direction, and so on. So, direction and magnitude both are changing. So, this is our magnetic field. We have created this magnetic field by properly putting all those circuits and currents and electromagnets, so that finally we get this kind of a magnetic field. What happens if a charged particle, say positively charged particle, is given a velocity and left in this region? So, if you have a uniform magnetic field, let us say this way, if you have uniform magnetic field and in the uniform magnetic field you project it, positive charged particle Q, then this is V, the magnetic field is going into it, V cross B, so V cross B, so going up, so this will be deflected upward, it is like this. So, if I see from this side, the magnetic field is going into the board, away from me, and the particle looks clockwise to me. Whereas, if I take magnetic field which is coming out of the board, so that when I look at it, the magnetic field is coming towards me, and if I project a particle with some velocity v, and this is v and b is coming this way, so v cross b, do v cross b, and you see that the force is downward and therefore it goes in this direction. So, let me make a rule out of here which I will be using in this case. If the magnetic field is coming towards me, and a positive charged particles make a circular motion, the motion will be clockwise. And if the magnetic field is going away from me and a positive charged particle is making circular motion, that will be anticlockwise. Okay? So, keep this in mind. And suppose I have a particle here and this particle is going in a circular path, If I see from this side, magnetic field is coming towards me, and therefore this should be clockwise. As seen by me, this particle should go clockwise. So, I have a small model to help visualize all these things. This is a bottle, part of the bottle, and it represents the magnetic field, which is strong here and which is weak in the middle. So, it is going like this, just like on the board. Then this particular thing I am just inserting it here, and this toothpick tells me that axis, which I will take at x axis. This is the x axis. The magnetic field is coming like this. So, see the right part of that. The magnetic field is coming like this, and then this is the axis, x axis, and this is the part which I have put it to show you the motion of the particle, charged particle, positive charged particle. So, if I see from here, the magnetic field is coming towards me, and therefore the particle should go in clockwise direction. So, it should go in this way. Suppose the particle is here at this moment, so it will go in this direction, this will be the velocity, right. Of course, this is not a uniform magnetic field, the particle is not projected perpendicular to the magnetic field everywhere. So, it will go in a spiral path, but nevertheless look at this point, from this it should be clockwise. So, the velocity is in this direction. Let us take my finger, this forefinger, as the y axis. So, here is the x axis, here is the y axis, and then vertically upward x here, y here, and then I cross j is k, that z direction is vertically upward. So, remember this, we will be using expressions, we will be using this to write expressions of velocity and magnetic field. This is x axis, here is the magnetic field, bottle type magnetic field, here is the x axis, here is the y axis, and the z axis is vertically upward, and here is a particle, and at this moment it is moving in this direction, it is moving in this direction. All right. So, now we have to write first the velocity, components of velocity. So, you can see that velocity here is just parallel to the y direction, positive y direction. So, you can write this velocity as v j cap, velocity as v j cap. Remember, I will go there on the board and write. Till that time we have to remember that the velocity of the particle here is v j cap. This is y direction, velocity is in this direction. Magnetic field. Now, the magnetic field is tangential to the bottle. These are the field lines, these are the field lines. So, the magnetic field is like this. What are the components? This is magnetic field, it has an x component parallel to this toothpick. This is the magnetic field tangent to this bottle, and then it has a component in this direction, and the other component is in negative z direction, is going down, vertically up is the z axis. So, it is going down. So, there is a component of magnetic field in the negative z direction. So, we will write our magnetic field as x component bx I cap, then bz with minus k cap, with minus k cap. So, remember our velocity is v into j cap, our magnetic field is bx I cap minus bz k cap. So, that is the kind of expression I am going to write on the board. So, I am talking of this point, it is going in a spiral path, it is going in a spiral path, but here let us see at this point v is v j cap and b is bx I cap minus bz k cap. What is the force on this particle here? What is the force on this particle here? The force will be q v cross b, and q v cross b will be q, v is v j cap and cross bx I cap minus bz k cap. Okay, so q into v, then j cap here, I cap here, j cap cross I cap is minus k cap. So, it is bx and then minus k cap. So, I have made this cross product. Now, make this cross product. It is q v. So, q here, v here, minus bz here. So, bz here and minus here, q here, v here, minus bz here, then j cap cross k cap, j cap cross k cap is I cap. So, this is I cap. This is the important point. This is the expression for which I have done all this algebra. You see that in this perpendicular plane there is a motion, definitely yes, but what happens to its velocity in the x direction? If it is a uniform magnetic field and there is a component of velocity in the direction of magnetic field, then it goes in a spiral path and this velocity component remains constant. So, helical path it just goes. But here the force has a component in x direction that is negative. So it is being pushed away from this neck. The magnetic field is pushing it back, this is the x component of force. The particle is coming ahead and this neck is pushing it back. All right. So as it goes ahead, and since it is all cylindrical symmetry, so it doesn't matter whether I take at this point for discussion or this point for discussion or this point for discussion, any point you take, and remember this is how it is going, you can see that the x component of the force will be away from the x axis. Towards the middle of the bottle, this x component of force will be. So as it goes towards this neck, the x component of velocity will keep on decreasing. The kinetic energy of the particle will not change. Magnetic forces cannot do any work. So Vx square plus Vy square plus Vz square will be constant, but Vx will keep on decreasing. And in proper situations, it could be that this Vx becomes 0, but if those Vy and Vz are there. So now the forces will be there and these forces will push the particle back. So after reaching here, it will again start coming towards this, and then it will go on this path, and then it will come once again on this side. Once again, when the particle is coming like this, this neck will do the same thing, and it will exert a force in the x direction now, and it will push the particle in this middle region. So ultimately what is happening? You have magnetic field. There is no material boundary. You have only magnetic field you have created in a region, and the charged particle you have injected there. The charged particle is trying to move. Then some of the charged particles having proper velocity, proper direction of projections, they will be confined in this bottle, they will be confined in this region, they will go to this side, this side, this side, this side, but they will not go out of this. So it is a magnetic confinement of the charged particles. Using magnetic fields, we are trying to confine the particle in a region. There is no material boundary, but still the charged particle can stay there for some time. Of course, not very long time. This is a very interesting project for nuclear fusion. How much time we can confine these very hot particles with high thermal kinetic energy, trying to fuse the particles and create energy from there, but nevertheless magnetic confinement is possible, and this is one example. All right, so we will stop here, we will take up something else next time.